Welcome to another Leetcode solution. Today we'll be looking at problem 272, closest binary search tree value, part 2. So there's already a part 1 of this problem, which is a simple variant of it. I have already uploaded a video on it. I'll link it down in the description. So let's look at this problem now. The problem says that we are given with a root of a binary search tree, a target value, and an integer k. Return the k values in the BST that are closest to the target. You may return the answer in any order. You are guaranteed to have only one unique set of k values in the BST that are closest to the target. In simple language, the problem is asking us to look through the tree and find max k values from the tree which are closer to target k. So let's look at the first example. So we are given a graph. Here is 4, 2, 5, 1, and 3. And the target here is 3.7. And we want to return two values which are closer to, or I would say most closer to the number 3. So solving this problem is possible in a couple of ways. We can probably use a heap. We can also use an array and do a sorting on it. And yeah, basically some other type of solving it like quick select. But the most efficient solution to solve this problem is to use a queue with max k values stored in it at a time and simply do a DFS on this graph. So without wasting a lot of time, let's just try to implement the solution. So we are going to use a queue in this case. Then we need to do a DFS. So we will be defining a DFS function, which would be taking the current node we want to traverse. And because we are doing a in order traversal of the tree, we will be looking at nodes.left first, then node.value, and then node.right. So how do we exactly process this left, then val, and then the right? So obviously we are going to do a DFS because the left side of the tree should be processed first in a in order traversal. So in order is nothing but our parent node value is inside left and right, so that's why it's called in order, right? So we do the DFS for node.left, and then we need to process the node value. So how do we do that? So for that, we are going to check if our size of the queue is less than k, then we simply add that value to our queue. So we say queue.append node.val. If that's not the case, it could happen that the queue is already having k number of items in it, and we want to push the new value into the queue only and only if it's more closer to our last value we had at the top of the queue. So let's see. So how do we compare that? That can be compared using the absolute difference between our topmost value in the queue and the current value. So we can say if absolute of q0, because we'll be having this at top, and actually just q0 minus absolute of target is greater than the absolute difference of the current value and the target. So you can see that I'm doing a target later, like I'm dividing or I'm subtracting the value from the target. It shouldn't matter because we are doing absolute here. Or actually, let me just simply put it in the right order. Just makes it easier to remember. Right, so we are doing absolute difference. Then again, or actually, I don't need to call absolute twice on them. I can simply say this, and I don't need that extra parenthesis as well. Same here, the absolute difference of target minus node val. So if this condition is true, that means we got the new value which is more closer to the last value we had in our queue. So what do we do in that case? We simply remove the value which was farther away from my target value. That we can do with pop left, and then we need to append the node.val. And remember, because this is also a in order traversal, a DFS, and we also need to do a DFS on the node.right. So if this works properly, we are having k values in our queue which would be near to our target value, and in the end we can simply return the queue. How do we do that? it's basically having the values correct in a correct form, or correct values in the queue. But the only thing that we need to take care of here is we need to return a list, not a queue. So that we can do by casting the queue into a list. So let's walk through the code and one of the example just to do a dry run. So we are given with a tree which is having values like this. Then we have our variables queue. Then we have basically we are not having a variable for this one, but yeah, let's just call it. Or actually we don't even need that. And yeah, everything is in queue. So queue is empty initially. Then we process the first route, which is something I just noted that we haven't called DFS on route. So it's always good to try run through the code before you actually run in an interview, because that gives you an idea of the bugs you might have left there. So we start the DFS with the route. Now we are entering the DFS method. We are going through the node.left before we start processing the value. So if you look at the graph, our left side is 2, and for that also we are going node.left, so we are going to 1. So because we have reached the end of the left side of the tree, and our queue is empty, which is less than the size we need, which is less than 2. Actually, let me also note down the k value here. So k is equal to 2. Because our length is less than 2, we are simply going to put 1 inside this. Now, because our DFS will return here, because there's nothing left on the left side anymore, we are back to the root, because this value was given to us initially. So now we check if the queue size is still less than k, which is true in this case. We simply append the value to our queue. Yeah, because this was true, this won't trigger, and then we go to the right side of the tree. So when we go to the right, we are still at the root, and then we are going to root the value at right, which is 5. So our current value, let me just put it like this here. So our current is 5. Now we check if the size is less than k, which is not the case in this one. So we see that now we need to check the difference between the target and the current value and the last value we had in our queue, which was 1 here. Right, so we what do we get here? So we do target minus 5, which is 3.7 minus 5. So I'm just putting down the comparison just to visualize it. Equal to 5 minus 2, or actually 5 minus 3.7, which would be 1.3, right? Yeah, 1.3. And then we have another value which is target minus node dot value. So node dot value was 5, and we need to do q0 value with the target. So our target is still 3.7 minus 1. So we get here 2.7. So we can see that the current the q0 is farther than the value we have currently on our call stack, which is 5. So what we do, we remove that value from the tree, from the queue, and then we put the new value in here. So far, following this call stack and this DFS, we are going to again go back to the node.left, and in the end what we'll be left with is 4 and 3. So that's what we see here. And yeah, I guess we're missing another return here, because if let's say this value was not close enough, then we also need to handle another else case where we simply return and we don't go to that path any longer. So yeah, that's pretty much it. Okay, looks like I did a blunder here. None type has no attributes left. That's because our root can optional. It could be optional or none basically. So we say if not root, then we simply return an empty list, because if there is no node, there are no closure values to it. All right, another problem. Oh yeah, because we are passing node.left, and node.left could be empty as well. So we say if not would say if node, then we do all of this. Otherwise, that's because like the leaf values could be none as well, so that's why it was complaining. Right, it's accepted. Let's try to submit it. Nice, it beats 100%, and because we are on a premium account, it says it gives us the time complexity automatically. But let's look at the time complexity in this case. So we are starting with the root, and we are pretty much processing all the nodes. Like we do a full traversal of the node, unless like there's a value which is not marked as closure. But still, the worst case complexity or worst case visiting will be all the nodes that we have in the tree. So that's why it's O of n. Even the memory, are we using extra memory? Yeah, we are using extra memory, but that will be having at max k number of items in it. So that's why we say. But there's one more thing. Because we are doing a recursive DFS, the node, the stack memory footprint of this DFS could be O of n as well. So both of them, including the time complexity and the space complexity, are big O of n. Yeah, that's our solution. Just curious, what does Leetcode say here? It says O of k, but worst case it could be O of n. So yeah, I guess that's fine and should be acceptable in your interview. That's it. Thanks for watching.